So we're going to try to put a lid on this whole functional limit thing, and we're going to try to get into continuity, although they are pretty intertwined, right? But showing here, okay, in the past, like we did like one example showing the limit of um, as x approaches c, right? As x approaches any sort of arbitrary c. I believe that's what it was. If you could permit me to go back, or rather, it was the limit as x approaches zero of the Dirichlet's function, right? Um, does not exist, right? And that was using just the negation of the definition of functional limit. Now we're going to use the divergence criterion for functional limits. Okay, we're going to basically try to come up with two sequences of the domain where each sequence is not uh, include, right? Each term is not equal to the limit point. Um, each of those sequence converge to C, and their image sequences converge to different values, right? So what does the graph of this function look like? I mean, that's helpful to draw, right? X is smaller than 0, it's going to be -1. X is bigger than or equal to 0, it's going to be +1. Um, so let's try to come up with two sequences that converge, but whose images, right? So basically, if we think about terms going this direction, okay, that are going to converge, okay, their images are always going to be what? They're always going to be -1. Okay, so that's going to converge to -1, and likewise, we're going to do the same thing here. We're going to go in this direction, basically. I'm going to pick x values here that converge to 0, whose images are going to equal to 1, and that's to complete the proof. So let's define x sub n. Okay, what's something that converges to 0? That's going to basically go in this direction. How about -1 over n, right? Uh, if we define it like this, okay, x sub n is going to converge to 0. F of x sub n, okay, that sequence is going to converge to what? Well, okay, each of these are negative, right? And so always f of x sub n, right? F of x sub n is always defined by whatever x sub n is. If x sub n is always -1 over n, -1 over n is always smaller than 0. Right, for all n in the natural numbers. So f(x) sub n is always going to be equal to what? It's going to be equal to -1, always. So this is going to converge to -1. Okay, now likewise, it's going to define y sub n is just going to be +1 over n. And that's going to converge to what? To 0, to the same limit point. Now f of y sub n, okay, the sequence, what does that converge to? Well, that's always going to be equal to what? F of y sub n, well, 1 over n is always it's always going to be positive, it's always going to be bigger than 0, so f of y sub n is always going to be 1. So this is going to converge to 1. We can clearly see that these are not equal, so by the divergence criterion for functional limits, the limit as x approaches 0 of f of x does not exist. Okay, going back to Dirichlet's function. Again, drawing a graph for this is kind of impossible, given how the rationals and the irrationals fit within the real numbers. Okay, but can we come up with a sequence x sub n where each x sub n, and I don't know if I made this clear or not in the past slide, right? Each of these x sub n's are not equal to 0, right? Each of these x sub n's and each of these y sub n's. I mean, but that should go without saying, right? Um, yeah, how can we define an x sub n here that's going to go towards 0? Um, I don't know. Let's say 1 over n, right? X sub n is going to go towards 0, right? F of x sub n at each 1 over n, right? 1 over n always, okay, for any natural number is going to be which one? Is it going to be rational or is it going to be irrational? It's going to be rational always. So that's always going to be equal to 0, right? So this sequence is really just the 0 sequence, which is going to converge to 0. Okay, now let's do y sub n. Y sub n, okay, we have to be a little bit more careful with how we define this, right? We still want it to converge to 0. We want each of those terms to not be equal to 0. Um, basically, we just want something when we take the image, right? The image of each y sub n, right? We want that to always equal to 1, okay? And that can be the case when each y sub n is going to be an irrational number. So let's think about a sequence where each term is irrational and it's going to converge to 0. How about square root of 2 over n? I'm pretty sure that that's always going to be irrational, right? Given how square root of 2 is an irrational number, right? Or you could really put in any rational number here. You could put pi or e or whatever, right? So that's going to converge to 0, right? If I evaluate the function at e over n, right, which is not a, right, e is a transcendental number, right? I believe. I'm not sure. But this entire thing is not a rational number, so this is always going to output to 1. So that sequence is just going to have a sequence of all ones that's going to converge to 1. These are not equal by the divergence criterion for function limits. Okay, the limit is x approach f of x does not exist. So really this is really an economical corollary, right? When you're able to find sequences that that belong to the domain A, right? That converge to the limit point, but you see that their image sequences don't converge to the same value. It's just like a nice way, right? When you're able to find sequences, it's not always the case, right? Okay, we're gonna do this question like super fast, because it's not that hard, right? Um, basically, okay, you can use sequential criterion for functional limits, right? Um, and so like you could argue basically using sequential criterion and then using properties of algebraic limit theorem for functional limits, okay, and find the limit that way. Okay. We're actually going to use the epsilon delta version, okay, and we're gonna kind of use like a like very heuristic version of the algebraic limit theorem approach, right? Like just like a very heuristic like calc 1 approach, right? So just factoring this guy, this is going to be what, x minus 3 and then x minus 2, okay? So these x minus 3's cancel out, right? So that's a removal continuity. This limit should, okay, it should be what? What's 3 minus 2? It should be 1. Okay. Um, so we want to show this, right? Using the definition of limit. We want to show that for all epsilon bigger than 0, there exists a delta bigger than 0 such that 0 is smaller than absolute value of x minus 3, right? Limit point is 3. Uh, Smaller than delta implies that the absolute value of x squared minus 5x plus 6 over x minus 3 minus 1 is smaller than epsilon. Okay, this entire thing, when x is not equal to 3, which is what we are assuming, it's going to be equal to x minus 2, right? I could go into detail about that, but I don't think it's that useful, right? Okay, so what do we get? X minus 3 is less than epsilon. Okay, we can make absolute value of x minus 3 as small as we want. Okay, so we're trying to go up this ladder, right? So far we have like a bunch of equivalent statements, but what would imply this is basically if we took delta to be equal to epsilon. Okay, so if we took, so now we're going to do the actual proof, right? So we're going to let epsilon be bigger than 0. We're going to pick, right, delta, oops. We're going to pick delta to be equal to epsilon, to equal to e, right, to epsilon. Oh my goodness, I cannot speak. Okay, so this is going to imply that absolute value of x minus 3 is smaller than epsilon. Absolute value of x minus 2 minus 1 is smaller than epsilon. Okay, and absolute value. Okay, so this x minus 2 expression, okay, is x squared minus 5x plus 6 over x minus 3. Okay, and the reason, again, why we can replace that is because, okay, we don't care about what happens at 3, right? This is only for uh, x minus 3, right, being in a delta neighborhood, okay, other than, uh, okay, and x being a point other than 3, okay, so that's what kind of allows us to do this, because if x was 3, okay, now you have 3 minus 2 here, 3 minus 2, okay, is 1, okay, but if 3 we plug in here, that's not going to be a number, right? Um, Okay, so then this is going to be a -1 type deal. Okay, and that basically shows that the limit as x approaches 3 of this function is equal to nothing other than, okay, 1. All right. All right, really trying to put a lid on this guy. Okay, so we could do this all day. Okay, so heuristics is going to say what? That there's a removable discontinuity at x equals 2. So if you factor out the x minus 2 here, you're going to get something like a x squared um, plus 2x, right? Plus 4, right, over x minus 2. And so if we don't care about what happens at x equals 2, we can cancel that guy out and basically substitute 2. And so we really want to show is that this guy is equal to what? 4 plus 4 plus 4. We want to show that this equals to 12, right? Substituting 2 into the expression. We want to show that for all epsilon bigger than 0, there exists a delta bigger than 0 such that 0 smaller than absolute value of x minus 2 smaller than delta implies that absolute value of the function, right, minus 12 is smaller than epsilon. Okay. If we don't care about what happens at x equals 2, we can argue that on this domain, right, that is just going to be x squared plus 2x plus 4, right? And then taking that away from 12, we're going to have x squared plus 2x minus 8, right? Since minus 12 is 8, right? Less than epsilon. I'm going to factor this into two different absolute values. So that's going to be x plus 4, and that's going to be x minus 2. I have a bound on x minus 2, right? I'm not too worried about that. I can make that as small as I want, right? Since I can pick delta to be as small as I want, okay? Um, if I suppose for a second that delta can be no larger than 1, then that means that x minus 2 has to live in between, right? Since absolute value of x minus 2 has to be smaller than 1, it has to live in between -1 and 1. So plus a 4, right, would mean I'm adding 6 to both of these, right? So 7 and then um, 5, right? And then seeing how this plays out, okay, absolute value of x plus 4, okay, if x plus 4 lives in between 5 and 7, then I'm bounding this guy above, right? It has to be smaller than what? It has to be smaller than 7. So given this is the case, okay, I can now replace this with a 7, because that's going to imply that, right? And so that's equivalent to saying absolute value of x minus 2 is smaller than epsilon over 7, right? And so basically I'm going to pick delta, right, to be the minimum of 1, right? So that's always smaller than or equal to 1. And then it's also going to ensure that absolute value of x minus 2 is going to be smaller than epsilon over 7. When both of these are the case, I can start this and then build my way up this ladder. Okay, let's go ahead and do this proof. So we're going to let epsilon be bigger than 0. Okay, and we're going to pick delta to be the minimum of 1 in epsilon over 7. Okay, then um, whenever 0 is less than absolute value of x minus 2 is smaller than delta, okay, we're going to have absolute value of x minus 2 is smaller than epsilon over 7, right? It's starting with what delta has to be smaller with in terms of epsilon, okay? Multiply this guy by 7, right? Arguing that absolute value of x minus 2 has to be smaller than 1, right, is going to essentially bound 7 uh, below by absolute value of x plus 4. Okay, so I can replace the 7 with the x plus 4. Okay, and then I just do the algebra that we're all very familiar with. I'm going to transform this to this, right? And then since I'm assuming that x is not equal to 2, I can transform uh, that x squared plus 2x plus 4 component of that, right, into this, okay, and then the remaining will just be a minus 12, right? And that'll be smaller than epsilon, and that'll basically complete the proof. I'm not going to show the details because it's kind of redundant. All right, got a couple more examples before we want to dive into continuity. Now, showing that this guy doesn't exist, okay, again, we can use a couple of different methods. Okay, let's try to approach this using the sort of, I already forget what it's called. It's the divergence criterion for functional limits. So we're going to find two sequences that converge to zero. Each terms are not going to be um, not going to have the number zero, right? And they're going to be terms consisting of elements of the domain, okay? And we're going to show that the image sequences corresponding to them are going to be different. Um, how am I going to consider this? If you think about the graph of this, okay? If you think about the graph of this, what does this look like? Basically, um, you know like the end behavior, it's kind of like tailing off towards zero, right? But then what's happening is uh, as you get closer, what's happening is that you're gonna have like a ton of oscillation, right? So it's gonna look kind of like boom, boom, and then there's gonna be like extreme oscillation, and you know, one can only draw this so accurate. But the idea here, okay, is going to be to come up with sequences of terms that are going to converge to zero. And because there's sort of infinite oscillations as you get to zero, okay, I can kind of like make terms, okay, that are going to have images that are going to be exactly the same, okay? And so that's going to be like my image sequence. So there'll be something like, okay, at some point each of these is going to be zero, right? And so if I can come up with a sequence that converges to zero, and the image of those is all zeros, okay, then the image is going to converge to zero, and then I'm going to come up with another, okay, sequence of terms that is going to converge to zero, but the images is going to be something else. It's going to be, for example, okay, it could be like one or something. I'm doing a terrible job of graphing this. These should all be level. But that's like the general idea, okay? And that's where I'm going to construct these two sequences. Okay, I don't think the drawing is too important, to be honest. Um, let's define x sub n. The way that I'm going to define x sub n such that it converges to zero and all the terms are not zero, I'm going to say, okay, because I can be strategic here, okay? So if I can make it so that always what's going to be in here is basically a multiple of pi, then the image sequence is always just going to be what? It's always just going to be zero. So if I make it 1 over pi n, right? So if I make this basically equal to this, right? Then what is f of x sub n, right? Each f of x sub n is going to be what? It's going to be 1 over the reciprocal. It's going to be the reciprocal of this, essentially. It's going to be pi n. Okay, first of all, we know that x sub n converges to 0. Okay, that should be pretty clear. Um, now this guy, okay, is nothing more, okay, for every natural number, okay, any multiple pi, the sign of this is going to be, yeah, this should be inside of a sign. Sign of the reciprocal of this. My apologies. So sine of pi n. Okay, so for every natural number, okay, sine of any multiple of pi is always going to be 0, and that's going to converge to 0. Okay, so in the graph, what you would have is like you would have those infinite sort of oscillations, right? And sort of you have a sequence where the image is just 0 as you approach 0. And there's infinitely many of these oscillations. So think of like a, what are those things called? Think of those accordions, right? You're just squeezing these like these sort of curves. The other sequence that I'm going to consider, okay, is now I want to try to construct something. I'm going to try to get like all of the images. Okay, my goal is to make all of them basically to be one. Now, how am I going to do that? Well, if you think about sine, when is sine equal to one, right? It's basically when it's like pi over 2 plus a 2 pi and basically anytime, okay, you're up here, right? And so that's going to be at pi over 2, right? This is sine of pi over 2, and that's also sine of I believe it's going to be 5 pi over 2, right? And so on, right? Now, there's probably a smart way to define such a sequence here where I want each term to be like, okay, pi over 2, 5 pi over 2. So I gave this quite a bit of thought about like how are we going to produce a sequence y sub n such that it converges to 0 and that each term is not 0 and each term is an element of the real numbers such that sine of 1 over y sub n would always be equal to 1, right? Because the idea is to come up with something different than our x sub n, which our x sub n was defined to be xn equals 1 over pi n, right? And we know that this converges to 0, and the reciprocal of this is always a multiple of pi, which would always be equal to 0, right? So f of x sub n, right, would go to 0. My goal here is to make f of y sub n, that this sequence, right, would always be equal to 1. This is sort of like my goal. Um, Now, I gave this quite a bit of thought, right? Because initially I had made like this crazy piecewise function where I used mod 4. Um, but there's actually a nice way to kind of always have this be the case. So writing out what I want is that I want the sign of the reciprocal of my x sequence to always be equal to 1, right? Just to try to get two different image sequence convergence values, right? Um, I said, okay, well, x sub 1, we would want that to be um, 1 over pi over 2, right? And so then sine of that, sine of sine of the reciprocal of this, right, um, would be sine of pi over 2, which would be equal to 1, right? And so 1 over pi over 2 is really 2 over pi, right? And if you do this for the x sub 2 and the x sub 3, you see that we want x sub 1 to be 2 over pi. We want x sub 2 to be basically have a denominator where it's 4 pi greater than the previous denominator, and basically that's the pattern, right? And so the way I'm going to define y sub n such that this is the case, okay, I'm going to say that y sub n is going to be equal to 2 over 4 pi multiplied by n minus 1. Notice how when n is 1, this entire thing is just going to zero out, right? Plus pi. Okay, so you can see how here the first term would be 2 over pi, the second term would have to be 2 over 5 pi, and so on. And so if we took each term of this guy, right, and these x's should really be y's, right? We already defined x sub n. But if we define y sub n in this way, first of all, we need to see that this clearly converges to 0. Okay, and that should be apparent, right? Based on the appearance of the n in the denominator and just nothing in the numerator, right? And this can be shown rigorously. But sine of, okay, what's going to follow from this is that sine of 1 over yn, right, which is basically your function evaluated at y sub n, right? So that sequence is going to be this, right? And so that's always going to be reciprocal of 2 over pi, so pi over 2, okay, 5 pi over 2, 9 pi over 2, and you'll see that this always equals to 1, so that's going to have that's going to essentially be a sequence that converges to 1. Okay, so we showed two different sequences. Okay, I erased this, but x sub n we had defined it to be, I want to say 1 over pi n or something like that, right? And so then f of x sub n, right, was essentially sine of pi n, right? And so that always kind of went to 0, and so that converged to 0. So we found two sequences, right, that converge to the limit point. Okay, each element of the sequence is an element of the real numbers, and it's namely not that limit points, namely not 0. And when we consider the sequences um, of their images, right, of their corresponding images, we see that we have two different values. Okay, so we would say by the, okay, I forget the name, but it's by the divergence criterion for functional limits, we conclude that the limit as x approaches 0 of sine of 1 over x does not exist. Last sort of problem. Okay, we're given a definition here, and this definition is very similar to a limit of a sequence diverging to positive infinity. Okay, this is to say that given any positive number m, okay, there's a there is a delta bigger than 0. Okay, such that for all, okay, for every single x in that delta other than a, okay, other than a, the values of that function at those x values are going to surpass m. Okay, there's a subtle reason why this is a for all and not for some. Okay, I'm not going to get too much into that, as I just learned about this today, and honestly, my knowledge of this is pretty shaky. But basically, what our goal here is to show that when this is the case, we want to show that um, this guy right here, okay, 1 over x squared plus 1, okay, is bigger than m. And in this case, the value of a is 0, okay? So what do we kind of are going to assume? We're going to assume that we know absolute value of x is smaller than delta. Like I can make that as small as I want. I can choose whatever sort of neighborhood to restrict um, the x values, okay, centered around the delta neighborhood of 0, okay? Um, So now what I actually want to do is I want to bound this below each time, because if I can find something smaller, then something bigger obviously has to be bigger than m. So what I really desire is I want 1 over x squared to be bigger than m, applying the reciprocal. And now I want x squared to be smaller than 1 over capital M. Okay. So now I'm going to try to bound it by something bigger, right? Well, x squared is nothing more than absolute value of x, absolute value of x, and I know I can make that as small as I want. Okay, so knowing that delta is going to be an upper bound for absolute value of x, I mean, why not just replace those with deltas? All right, so we're going to choose delta um, to be essentially, so let me work this out, right? Delta squared is smaller than 1 over capital M, so applying the square root, right? Um, delta would have to be smaller than 1 over the square root of m, right? But I can actually just pick delta to be 1 over the square root of m, right? Since that being equal to 1 over square root of m um, would make delta squared equal to 1 over capital M, right? And so absolute value of x is smaller than delta, right? So replacing both of those deltas with absolute value of x would make this true, okay? But that's not an integral part of this proof, right? Whether it's a less than or equal sign here. But basically, okay, the way this formal proof is going to go is we're going to let m be bigger than 0, and we're going to pick a delta, okay, um, equal to 1 over the square root of m. Okay, now we need to make sure delta is positive. Okay, well, square root of a positive number is still positive. Okay, reciprocal of that of a positive number is still positive. So we're like totally fine to like pick delta in this manner. Okay. Um, and basically all of this is gonna follow now, right? So um, absolute value of x, right? Or I guess when this is the case, right? So 0 is smaller than absolute value of x minus a minus 0, right? Which is equal to absolute value of x is smaller than 1 over square root of m, right? Which is just delta. We're gonna have absolute value of x. Absolute value of x is going to be smaller than delta squared, so that's going to be 1 over m, right? So x squared is going to be smaller than 1 over m. 1 over x squared is going to be bigger than m. So 1 over x squared plus 1 is going to be bigger than m for any m bigger than 0. So there is that delta. Whatever m you throw at me, I'm just going to take the square root of that and then take the reciprocal. That's going to be my delta for where every single x inside of here is going to imply this. Okay. All right, we get to put a lid on functional limits. We're going to get into continuity now.